In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about the subsection of standard electrostatic configurations. As we discussed at the beginning of this chapter, the hard part about the electromagnetism is applying the ideas, not understanding them in this section. We will therefore summarize the important charge configurations that frequently appear on the exam. Now I want to go through the point charge. The force, electric field, and potential due to a collection of point charges can always be found by summing up the Colombo terms for each charge in the system. Problems generally fall into two types. In the first step, you are given an arbitrary arrangement of charge, and you need to find the force, electric field, or potential due to the charge at some nearby point in space. It is always best to start with symmetry considerations to limit the calculations needed. For example, if the point charges are at the vertices of a regular polygon, then the field and forces at the center will be zero because all components will cancel. Only after using as much symmetry as possible should you start writing down terms. If possible, you want to find the potential first and only then calculate a field by checking a derivative, since scalar addition is much simpler than vector addition. Figure 2 illustrates electric dipole. Figure 2.3 illustrates Gaussian pillbox for calculating the field of an infinite charge sheet. In a second common class of problems, you are asked to define the electric field or force of some configuration at a point very far from the origin. A standard example, which we will treat in a different context in section 2.4, is two-point charge separated by some distance. Suppose we have a charge q and a charge q separated by a distance 2d, and choose coordinates such that q is at d00 and minus q is at minus d00, which is related to the figure 2.2. The potential at some point is 0, and the x-axis is Vx is equal to 1 divided by 4p epsilon 0 multiplied by q divided by absolute x minus 3 minus q divided by absolute x plus d. Taylor expanding this expression for X is very bigger than D tells you approximately how the fields behave far away. Note that the lowest order terms in the Taylor expansion cancel, but the next non-zero term, the Taylor series, doesn't vanish and gives a much better approximation. Now I want to go through the planes. The classical example here is an infinite flat sheet of charge with surface charge sigma. By symmetry, the field must be constant in the magnitude. The sheet is infinite, so there is no local measurement you can do to tell you how close you are to it, and it looks the same from every distance. Again, by symmetry, the field must point perpendicularly away from the sheet, since that is the only preferred direction in the problem. Now we draw a Gaussian pillbox surrounding part of the sheet, which cuts out an area A, which is related to figure 2.3. The thickness of the pillbox doesn't matter because, as we argued, E has constant magnitude. The integral in Gauss's law is phi E dot ds is equal to 2 absolutely or 1 from each of the two opposite faces of the pillbox. The charge enclosed is q is equal to sigma I, and solving for E, we find E is equal to sigma divided by 2 epsilon 0 ampere. Ampere is a unit normal pointing away from the plane. This particular result shows up so often that it is best to memorize it, so we have given it an equation number you will see below in section 2.1.5. How precisely this same argument can be used to get the boundary condition for E at a surface. Now I'm gonna go through the line charge and sealants. Problems involving infinite line charge and sealants are usually solved with cylindrical Gaussian surfaces, for example, consider the electric field due to an infinite line of charge with charge per unit length lambda, which is related to figure 2.4. The field of a point charge points radially outward, but here we have an infinite line charge. By symmetry, the field cannot have a component along the line, and by the Maxwell equation, delta multiplied by E is equal to 0. The only option is for it to point in the arbitrary direction in the cylindrical coordinates from Gauss's law applied to cylindrical of height L and radius L surrounding the line. We have absolute E 2p RL is equal to lambda L divided by epsilon 0. Absolute E is equal to lambda divided by 2p epsilon 0 R. E is equal to lambda divided by 2p epsilon 0 R multiplied by RP. Notice that the height L of the cylinder cancels out when we express the result in terms of the linear charge density lambda. Spherical surfaces. Concentric spherical surfaces are another common geometry in electrostatic problems. Similar to the case of the cylinder, solutions can usually be obtained by using a sphere as the Gaussian surface to compute the electric field at each radius. Example 2.1 and 2.2. Now I want to go through the 2.1.5 boundary conditions. In the previous section, we learned everything needed to calculate electric fields and potentials in the bulk of a region, such as inside or outside of a sphere. But what about on the boundary between regions? Figuring out how fields behave on boundaries between regions of space is so important that it deserves its own section. Luckily, like everything else, it too follows from Maxwell's equation. Let's say that we have a continuous surface surrounded by vacuum and we zoom in so close that the surface appears flat. We now have a plane which we can use to define E. Parallelly, the two components of the three components vector E that are parallel to this plane. Add E perpendicular, the third component perpendicular to the plane. Mind the notation E parallelly is bold because it's a two component vector, but E perpendicularly is a one component scalar. Next, let's integrate or a narrow rectangular path with long edges parallel to the surface and short edges perpendicular to the surface using the second of Maxwell's equations in integral form. Equation 2.10. The line integral implies that E parallelly out minus E parallelly in is equal to 0, where E out is the electric field just outside the surface and E in is the field just inside the surface. This is true since the length of the path perpendicular to the surface can be taken to be arbitrarily small, and the other two opposite sides of the rectangle contribute equally and opposite in the integral. Let's consider the same surface but integrate over the surface of Gaussian pillbox and use Gauss's law equation 2.9. If we take the highest of the box to be extremely small, then using the same arguments as in the plane symmetry discussion in the previous section, we end up with the condition that E outside perpendicularly minus E inside perpendicularly is equal to sigma divided by epsilon 0, where epsilon is the surface charge density. Equation 2.14 and 2.15 let you patch together electric fields in the different regions of space across surfaces where strange things may be happening. A simple classic example of why this is useful is the case of conductors, which we discussed below in section 2.1.6. Before we do that, however, we should talk about how the potential behaves at boundaries, since working with the potentials is almost always easier than working with the electric field. It's not difficult to show the equation 2.14 and 2.15, and the fact that E is equal to minus delta V imply that V is always continuous. Similarly, the first derivative of V is concentrated so that derivatives of V are continuous except at short surfaces. These rules for the potential and electric field boundary conditions will allow you to match solutions across any type of boundaries. Now I want to go through the 2.1.6 conductors. While the GRA might throw a question or to your way that relies on knowing formal aspects of boundary conditions, you are most likely to use this idea when solving problems involving conductors. An ideal conductor is a material where charge can freely without resistance. Usually, metal and conductor are synonyms. For the purpose of the GRE, there is only one fact you really need to know about conductors. V is constant throughout a conductor. From this fact, you can derive four important corollaries. The first one is the electric field inside the conductor is zero. The next one is the net charge density inside a conductor is zero. The next one is any net charge on a conductor is confined to the surface. And the next one is the electric field just outside the conductor is perpendicular to the surface. These properties are direct consequence of the fact that an ideal conductor has no resistance to the movement of charge. If there were any bulk electric fields, a free charge would experience a force until they had arranged themselves to cancel out any electric field. On the GRE, you will occasionally work with grounded conductors. Usually, conductor is said to be grounded if it is connected to the reference for the electric potential. In other words, something is grounded if it is connected to voltage is equal to zero. You can think of this as setting the constant reference scale for the potential. The other important property of the idealized ground in electrostatics problems is that it is an infinite sink and source of charge. So if you put a charge near a grounded conductor, some charge will be induced on the grounded conductor with no cost in energy. See example 2.3. Now I want to go through the 2.1.7 method of image. These examples that we have discussed so far have been simplified by totally spherical, cylindrical, or planar geometry, which allows us to use simple argument with Gauss's law. Figure 2.8 illustrates setup for the method of image. As you might imagine, solving the potential and induced charge of configuration without this kind of total symmetry can be extremely complicated. In general, this is certainly true, but there are many tricks for symmetrically dealing with more complex geometries, particularly involving conductors. The only one of these methods that you are likely to need for the GRE is the so-called methods of image, which relies on the property of Laplace equation 2.7, the uniqueness of solutions. If you can guess the potential V and it satisfies the boundary conditions, it must be the correct answer. Consider the case of a point charge distance d above an infinite grounded conducting plane. Figure 2.8. Naively, this looks complicated. The point charge induces some complicated surface density of charge on the conductor. The arrangement doesn't have spherical or planar symmetry too, so we cannot rely on Gauss's law easily. But note that the potential on the surface must be constant because the surface is a conductor and it must be zero because the conductor is grounded. Now switch gears for a moment and imagine a totally different charge distribution, that of the original charge q and so-called image charge is minus q at z is equal to minus d. Figure 2.hp. The potential on the plane z is equal to 0 is exactly the same, namely v is equal to 0 for these two charges as in the case of the conductor. Furthermore, if we restrict ourselves To the region z is greater or equal to 0, the sources are for Poisson's equation are also the same, namely a single point charge q at the z is equal to d in both cases. Therefore, by uniqueness, the potential V produced by the charge and the image charge must be the solution to the original problem with the conductor, since it satisfies the same boundary condition at z is equal to 0 with the same resources. The essence of the method of image is this: whenever we have a conductor, if we can find an arrangement of point charge that exactly reproduces the potential on the surface, then the potential everywhere will be the same as if there were no conductor. But you must beware to place image charge only below the conductor in the region that would be inaccessible in the original setup. If you place them in the same region as the original charge, you would be adding different sources to Poisson's equations and solving a different problem. The only example you're likely to encounter on the GRE is in case of grounded conducting infinite plane from the sum charge on one side. In this case, for each charge, just put an opposite mirror charge on the other side of the plane at the same distance away, and you will have the potential immediately. While it is good to know this prescription, understanding why it works more generally is important and might come in handy for other problems. There is one very important subtlety about the method of image when calculating anything involving work or energy. Remember that there is no energy cost to moving an image charge. The image charge is just a fake construct, a trick to get the correct potential. In reality, there is no field below the conductor, and so no work can be done on anything below the conductor. This can get confusing because the position of the image charge depends on the position of the real charge. If you move the real charge in towards the conducting plane, the image charge moves with it. But work is only down on the real charge. A useful mnemonic that lets you forget about this subtly it is to calculate the electric field directly from the image configuration. In other words, don't calculate the electric field by taking the derivative of V, because doing so will implicitly count the motion of the image charge as contribution to the energy. A more detailed discussion of this topic can be found Graffiti and section 3.2.3. Thank you so much for watching my tutorial video on today. Today is the 15th of April 2026. Time is 12:50 a.m.